welcome back. I'm Pi, and today we're going to be going over some more problems from the 2020 and AMC 10A. This problem takes up a lot of space, but it's quite straightforward using simple logic. Tom has a collection of 13 snakes, 4 of which are purple and 5 of which are happy. He knows that all of his happy snakes can add, none of his purple snakes can subtract, all of the snakes that cannot subtract also can't add. So I'm looking at happy, which can add. Happy means they can add. Purple means they cannot subtract. If they can't subtract, according to this condition number 3, they can't add. Combining these two statements, I can use my answer choices. Purple snakes can add. A is incorrect. B, purple snakes are happy. We don't know this for sure, and this is incorrect because happy snakes can add, but purple snakes cannot, so B is wrong. Snakes that can add are purple. Well, we don't know this either, considering the previous statement. Happy snakes are not purple. We do know this. Happy snakes cannot be purple because happy snakes can add and purple snakes cannot. So that is our answer, and we can go over E just to check. Happy snakes cannot subtract. Happy snakes can add, but there's nothing about adding leading to subtraction here, so we can't make that conclusion either. So there we go. Our option is D. For our next problem, we can use some common facts about terminating and repeating decimals. So when a student multiplies the number 66 by 1.AB, which goes on, he doesn't notice the notation. He just multiplies 1.AB. So without the repetition, he just multiplies that terminating decimal. And then he finds out that his answer is 0.5 less than the actual answer. So we can rewrite 1.AB as 1 plus, and then this point AB part is just going to become AB over 99. Which you might have learned in your algebra class. And then we know that 1 point AB is going to be 1 plus this point AB without that repeating bar. And that's just going to be 1 plus AB over 100. So let's see. We know that 66 times what he did, 1 plus AB over 100, is 0.5 less than 66 times 1 plus AB over 99. So I'm going to subtract 0.5 from here. Just for convenience, let's call this number ABX because we know that they're 2 digits. And so it's just a 2-digit number. So now I've got 66 plus 66x over 100 plus 1/2 equals 66 plus 66x over 99. And I can just use some algebraic manipulation to get that 100x minus 75 equals 99x. And I find out that E is the correct answer because x equals 75. This next problem is algebra. And there's a couple ways to go about it. You can do guess and check, but I would really just use algebraic expansion and then take a look at that equation. So let's expand this out into x squared y squared minus 2xy plus 1 plus x squared plus 2xy plus y squared. Recall that a plus b whole squared equals a squared plus 2ab plus b squared. All right, now we can add this up, and we notice that some terms cancel. We've got x squared plus y squared plus x squared y squared plus 1. And this is actually very factorable. So let me rewrite this as x squared plus x squared y squared plus y squared plus 1. And I'm going to group some terms right over here. I'm going to factor out that x squared. I'm going to say this is going to be 1 plus y squared. And this is going to be 1 times y squared plus 1. And by the commutative property, 1 plus y squared is equal to y squared plus 1. So I've really got x squared plus 1 times y squared plus 1. And that's what I factored that into, this earlier expression. And so using this, I can say, wait a second, x squared is always going to be greater than or equal to 0, and y squared is always going to be greater than or equal to 0, given that x and y are real numbers. So this is called the trivial inequality. The trivial inequality says that this square is always going to be greater than or equal to 0. And so the least possible value of each of these expressions is going to be 1, and that occurs when x and y are 0. So multiplying them together, I see that it must be greater than or equal to 1, and so the least possible value of the whole expression is 1. In fact, this can also be done with partial derivatives in calculus, but in the spirit of the AMC 10A, I think we would just stick to simple algebraic concepts.